Alright, in this video I'm going to go through solving a 3x3 matrix using trying to get it to row reduced echelon form. So down here I have what the goal is, because here's our goal when we're trying to do row operations to a matrix. To get it in this reduced row echelon form, we want a 1 in the first entry up here in the first row, first column, zeros beneath it. We want a 1 in the second row, second column, with a 0 beneath it, and we want, if possible, a 1 in this next one. And I put number symbols here just because we don't care what's in these other places. I guess we do care if it's reduced row echelon form, we would want these other ones to be zeros. If we just go to row echelon form, we don't really care what these ones are, we just want these ones down that diagonal. So let's say we're starting up here with this system of 3 equations. We'll put it into an augmented matrix like this, and if you want to, you could draw a little line to augment the right side of the equal sign from the left side. So I'm going to start my row operations. You need to do it in the correct order. It's kind of like doing a Rubik's Cube. I tell my students, if you don't do it in the right order, you might mess up something you've done before. So we like to work in a certain order, and so we want to get our first one up here. So I'm going to do that. There's a multiple of ways you could do it, but I'm going to do it by taking row 1 and subtracting row 3 from it. That way 5 minus 4, I can see that's going to be a 1. And I do that to every single entry in the row, not just the one that I need, but I need to take negative 6, subtract negative 3, I need to take 1, subtract negative 1, and 4, subtract 5. So after doing that, here is my new row 1. And it has the 1 where I need it to be, right there. So after I get that 1, I'm going to work on its column. I'm going to be trying to make this 2 into a 0 and this 4 into a 0 in its column. So again, there's multiple ways you can sometimes do this. You usually try to look for one of the simplest ways. So down here I'm going to, I might cut this off a bit. Here we go. I'm going to take negative 2 times row 1 and add it to row 2. So I'm going to do, just to save time, work on the third row as well. Negative 4 times row, add it to row 3. Notice if I take negative 2 times 1, that's negative 2, add it to the 2 here, that's my 0. So that's where I got my negative 2 from. And I do kind of the same thing with my negative 4. I chose that because when I times it by 1 and add it to the 4 here, I'm going to make a 0, and remember, that's our goal. So if I do that, and I don't just do it on this column, I do it to every single entry in the rows, so these are row operations, it kind of changes everything here, but I have my 1, 0, 0. Now that I have my first column like it should be, I'm going to work on my next column. And remember, this one up here, we don't care what it is, we just want to start with working on this entry right here to be a 1. Right now it's not a 1, it's a 3. So to make it into a 1, the easiest way I can see is to divide everything by 3. Same thing as timesing by 1/3. So if I take 1/3 times row 2, it's going to change every entry in that row. Everything in row 2 just got divided by 3, so it became this right here. And so I have my 1, which is in my goal. So after I get that 1, I work below it and I try to get a 0. So I have this 1, I need this 9 to be a 0. So how about I take row 2 times it with negative 9 and add it to the row 3. That way a negative 9 plus a 9 would be 0. If I do that to every entry, I'm going to get my third row to look like this. Now, that's not really what my goal looked like, is it? Because this row actually zeroed out. I got zeros all the way across. Now, if you get zeros all the way across, it's still a consistent matrix. It's not inconsistent. It's consistent. It implies that 0 equals 0, and that's true. If you get something like 0 equals 4, that's not true. That would be inconsistent. But what this means is that we have a dependent system. So the solutions, you remember the whole goal of this was to figure out what x, y, and z were equal to. Well, in this sort of a system where you get zeros along all the entries in a row, it's dependent. Oops, that erased. It's dependent, so this one is in the z. Down here we have z, 0z equals 0, which means z can be anything. So this system is dependent on z. There's an infinite amount of solutions, but they are all dependent on whatever z is. So again, to rephrase it, if the last row ends up zeros, what we're going to do is put the variables back in, with their equal signs. We know that 0 equals 0 is true, so that's a dependent case. Let's figure out the solutions on this next slide here. So if I try to go one step further, just to get a 0 above the 1 in the second column right here, it'll just make it a little bit easier as I go and try to solve. So it's kind of along the lines of going to reduced row echelon form. But if I put a 0, do a row operation here to get a 0, I'll do that by taking positive 3 times row 2 added to row 1. That way 1 times 3 is 3, added to negative 3 would be 0. That'll get a 0 in my box up here. So now I have reduced row echelon form. Now let's put our variables back in. This was our x column, this was our y column, this was our z column. Over here was our answer column. So if I put them back in, I get 3 equations that look like this. I have 0 equals 0, or basically z equals z, or sometimes you'll have it z equals t if you let your parameter equal t. Right here we have 1y minus 1z equals 1, so that's where we got this equation. And up here we had 1x minus 1z equals 2. Now again, you could have done it up here, you just would have had an x, a y, and a z, and so it would have been a little bit more tricky to solve for. So we know z equals z, or you could say z equals t. And then for each of these equations, just solve for x or y, but you won't have a simple number as your answer, you'll always have a z in there still with your answer because there's no restrictions on z. So if we solve for x and y, get the x alone, get the y alone, you'll notice, yep, there's still a z in our answer over there. Yep, there's still a z, and that's what's supposed to happen because x is dependent on z, y is dependent on z, and z, turns out, could be any value for this problem since it didn't have any restrictions on z. It wasn't a word problem or anything. So again, that's what it means to be dependent, and your answers should be, you know, solve for x, and there should be a letter still in that answer over there because it's dependent on that value, and y is dependent on the value of z. And so it's an infinite amount of solutions, but they all have to follow this. So we could say maybe z is 2. Well, that would make y would have to be 1 greater than 2, so y would have to be 3. And x would have to be 2 greater than 2, so x would have to be 4. That would be one example of a solution to this system. But there are many, many others out there as long as they follow this pattern. So hopefully that helps with this solving dependent systems, and good luck with your homework.